Okay, so thank you for coming again to another installment of the Quantum Fluids and Isolation Seminar. So today we have Professor Leonid Levitov, MIT, speaking. So Professor Levitov got his master's degree of physics at Moscow Technical Institute in 1985. He got his PhD at the Landau Institute in 1989. And he joined MIT in 1991, becoming an associate professor in 1996 and a full professor in 1997. He's published over 100 referee papers and reviews in quantum transport, cold atoms, solid state quantum computing, graphene, and other fields. And you might know him as the namesake of the leviton, the quasi-particle found in certain 2D metals. So please help me in welcoming either by unmuting yourselves or by clapping virtually, Professor Levitov.
Yeah, no, thank you. Thank you very much for this kind of invitation and giving me this opportunity to speak. So what I want to talk about is the two-dimensional electron systems and how hydrodynamics, what kind of hydrodynamics we have in the systems. Two-dimensional electron systems have been in the focus of interest for a long time because interactions between electrons in the systems are much stronger than in 3D because Coulomb interaction is unscreened. It's a 3D Coulomb interaction goes in the 3D space and then comes back to 2D. And because of that, strongly interacting system expected to behave in a hydrodynamical way, so that electrons collide with each other frequently and exchange momenta and exchange energies, and collisions are high frequency. And so that's the intuition. And so based on that intuition, the experiments have been done and the hydrodynamic behavior has been found. And then after that happened, this was about 3 or 4 years ago, been questions whether the hydrodynamic behavior in two-dimensional electron systems is different in any way from that in high-dimensional fermion systems like helium-3, for example. And so what the essence of what I'm going to talk about in this work that we were doing in the last couple of years is to show that that yes, indeed, there is something quite different in how two-dimensional electron system becomes hydrodynamical as compared to 3D to 3D systems. So it will be two-dimensional fermions, and there will be Fermi surface. But because it's two-dimensional, there will be some new aspects that will change hydrodynamics to what we know from Navier-Stokes equation and so forth, to something quite different. And so that's essentially the punchline. Now let me see if I can. Yeah. All right. So maybe to start, let me talk for 5 minutes about how collisions look in the Fermi sea and what we expect classically, so to speak. So in the Fermi sea, you have states, many states occupied by fermions. The states with low enough energy, which are deeply submerged in the Fermi sea, deep below the Fermi level, they're occupied by particles, but because they're low enough energy, they don't play any role in action, which is all happening near the Fermi surface. And because of that, the quasi-particles which are here, this is schematic for electron dispersion relation, they're kind of spectators to what's happening near the Fermi surface. And then near the Fermi surface, there are low energy excitations with energies of order kBT, and usually in the systems of interest, temperature, thermal energy is much smaller than the Fermi energy. Can be comparable, but for the sake of simplicity, let me just focus on the case when it's much smaller. So it's what's called near degenerate state, and all states over here will be degenerate, filled with fermions and completely inert, and then states here will be active, and then that has been studied and for quite some time. And what textbooks tell us is that there are relatively long lifetimes for collisions between quasi-particles near the Fermi level, and they are long basically because there is a very small phase volume for collisions, and they are as long as 1 over temperature squared. So when temperature becomes small, then these collision times become pretty long, and so that's and then all the hydrodynamic behavior, let's say in helium-3, the benchmark three-dimensional Fermi liquid in which hydrodynamic behavior has been thoroughly tested in the past. I mean, hydrodynamic behavior unfolds on timescales longer than that collision timescale. And then on these longer timescales, there is notion of viscosity and transport coefficients, and all obey conservation laws and altogether form a hydrodynamic system. Now, what we're going to argue is that in two-dimensional systems, there are modes with even longer lifetimes. So there will be modes with the Landau time scale. So this inverse t square is due to a restricted phase volume. Explanation of that is due to Landau theory of helium-3. The longer time scales are not expected in the framework of Landau theory. They come in a somewhat different way, and so that's what we're going to discuss. And they, along with the normal modes with normal lifetimes, they will play a dominant role in the story. And because there are several different time scales, the whole behavior will be quite interesting. There will be a hierarchy of several timescales and a hierarchical structure both in time domain and spatial domain. Also, there will be interesting angular memory effects. So these new modes with long timescales, they actually have lots of interesting consequences and define surprising collective behavior in electron fluids and two-dimension that we're going to study. But I mean, to start, let me just review for those who want to see it again, and even for those who don't, review the standard phase space argument, saying that if I have a quasi-particle with energy epsilon above the Fermi level, and by collision it passes energy to, let's say, creates a particle-Hall pair out of continuum, it goes down in energy, and the rate for that process I can calculate just from golden rule rate, Fermi's golden rule transition rate formula, taking into account that these states are filled, these are vacant, and so forth. So putting in these Fermi occupancy factors, and then doing the calculation on that. If you think about what's going on geometrically, you can think, if you watch my hands, you can think like two particles, particle above the Fermi level, particle below the Fermi level. The phase volume for that you can calculate from this picture, and you see that it's proportional to delta epsilon, to the energy difference between to the excitation energy in the particle-Hall pair. And then if you take that and then integrate over all the energies that you can pass to particle-Hall pair, and these are the energies from 0 to epsilon 1, then integrating epsilon over the epsilon up to epsilon 1, you get epsilon square. And if that epsilon square if you do it at finite temperature, then epsilon square will become t square. So that's the explanation for that how phase volume constraint leads to that slow relaxation time near the Fermi level, right? And so that phase volume that constrains energy does not have anything to do with momentum conservation. So the two-body collisions are both energy conserving and momentum conserving. But when we talk and think about this Landau phase volume argument, we don't think about momentum conservation at all. And the reason is that in 3 dimensions, even though momentum is conserved, it does not restrict phase space, because if you can please watch my hands, if I have two electrons with momenta at an arbitrary angle to each other, and they're colliding with total momentum being conserved, then they can just do this. They can rotate about their common momentum angle, and in this way they can scatter on the Fermi surface by an arbitrary large angle, change the angle by an arbitrary large amount without breaking momentum conservation. In 2 dimensions, it's going to be quite different, and because of that, angular relaxation is going to be a bottleneck for some processes, and because of that, some revision of Fermi liquid, will be required, and that's what we're going to do first. We'll talk about first, and then apply it to hydrodynamics. Right. Okay. So right. So that may be an important slide to show. These are all the collaborators who contributed in this work. 3 students: Patrick, Lev, and Hao Yu, and they all now Harvard, and then the longtime collaborators, Andrea and Grisha from UK and Israel. So, right. So then, I mean, before we proceed, actually, how are we going to do it? Are we? What's the plan? Are we taking questions in the middle of the talk, or waiting till the end? It's not a large audience. There are only 20-something people, so we can probably do it during the talk.
Yeah, it's up to you.
Whatever you say. You're the boss.
Oh yeah, if anybody wants to ask a question, if it's okay with Professor Levitov, just feel free to unmute yourself.
No, it's more than okay. Actually, please do ask questions, and otherwise I won't know where to go. Yeah. Okay. Good. So looks like all clear so far. So let me explain how I was thinking about these angular constraints. And maybe to start with, let's start with a two-body collision when 2 particles are colliding, and then there are no other particles around. So it's happening in free space, and there is no Fermi sea. All pretty simple. Then we know how to solve that. We go to the center of mass frame, and in the center of mass frame, every collision becomes a head-on collision. We have 2 particles coming head-on onto each other, and they can scatter at an arbitrary angle. And because energy is conserved, all the states of particles that you can get in this way, they are somewhere in that kinematic circle that you draw on the diameter, taking the momentum of the incoming particles, and then particle 1 can scatter here, particle 2 can scatter there. So long as they remain on that kinematic circle, they can really go anywhere, right? But now let's think about what happens if these two particles, 1 and 2, are part of the Fermi sea, and they're somewhere near the Fermi surface, and because of that, we have to draw that kinematic circle and superimpose it with the Fermi sea, and then we find that a large part of that circle is actually inside the Fermi sea. So that means that these states are populated, and particles cannot scatter onto that part. That means that they cannot scatter on that part also, and that means that out of that kinematic circle, the only available phase space in that is in the pink region, the band of states which are thermally excited within kT from the Fermi level, and that means that the angle change in scattering can only be as small as that over the kBt divided by Fermi energy, and that's a pretty small number. So if that was right, so that means that the angular relaxation on 2-body collisions is quite constrained, and if that was so, that's an observation number 1, and then if that was all the story, then I think we would conclude at this point that there is very strong angular memory in a 2-dimensional Fermi gas, and collisions happen, but maybe they relax in help to relax energy, but don't really help to randomize angles, and therefore hydrodynamics cannot occur because particles cannot change orientation of their momentum by more than that much, and that's a very small number when temperature is low. So that basically would tell us that hydrodynamic behavior is very hard and maybe impossible, even impossible to achieve. However, what I told you is only part of the story, and then you can ask, are these processes that we considered, the generic angle collisions that in which angular relaxation is very small, is this the only possibility? Can there be some other processes which relax angle more efficiently, right? And then if you think about that, you can see that if you consider processes in which particles collide head-on, as shown on that schematic, then and take particles 1 and 2 and draw kinematic circle, then kinematic circle will coincide with the Fermi surface, and as a result, I can get the outgoing states positioned anywhere. Kinematically speaking, I can get them positioned anywhere on the Fermi surface, and for head-on collisions, therefore, angular relaxation does not present a bottleneck. So we have to look into rates and compare how efficient and what are the rates for these processes and for those processes. And for angular relaxation, the head-on processes will be highly efficient. So if their rate turns out to be, appreciable, then they will dominate in the hydrodynamic behavior. And then if you do calculation, you find that actually the rate for these processes surprisingly is the same as in Landau Fermi liquid story. It's T square. So there is no, even though it might seem that these processes are a little bit constrained in phase because they're happening, everything is happening head-on, the rate is unchanged, and it's T square just as in three-dimensional Fermi liquid. And because of that, what's going on, if we want to consider, hydrodynamic limit when particle momenta are rapidly exchanged and their orientations are randomized, will be dominated by these collisions, right? And so that's kind of the story. And then if you want to make it more precise, you want to think about distribution function and decompose distribution function into the even parity and the odd parity parts in momentum. Take distribution function which describes deviation from the equilibrium state on the Fermi surface, and then you can introduce the even and odd components, and then thinking about which processes contribute to relaxation of the even ones and the odd ones, you realize that the even ones will relax due to head-on processes, and the odd ones cannot relax due to head-on processes, because if you have a particle here, then in the odd distribution function, particle here must be accompanied by a hole here, and then the particle will have nothing to scatter on. So the odd parity harmonics of the distribution function will be relaxing very slowly, much slower than the Landau T-square law tells us. And the even parity part will be relaxing at a normal rate. So that means that not only there will be, transition from ballistic behavior to some kind of ergodic behavior on the Landau timescales, which correspond to these processes, but on top of that, there will be some long-lived modes which are due to the odd parity part, and so it will be not just a simple hydrodynamics, but hydrodynamics with many slow degrees of freedom built into it, and so that's kind of where we're heading. And then if you make it like even more precise and decompose the distribution function into harmonics, into cylindrical harmonics by interpreting distribution function geometrically as a distortion of the shape of the Fermi surface, like shown in this picture, can introduce angular harmonics of different order, and then the odd ones will be long-lived because they will be, their relaxation is governed by the by generic collisions that which are not head-on, and these collisions, the angle change can be only very small, whereas in the even parity harmonics, the relaxation rate will be t square. So we have, and then of course there are normal hydrodynamic, like conventional hydrodynamic modes, which are infinitely long-lived in the absence of disorder because they correspond to particle density and momentum density, and they are conserved in two-body collisions. And so the usual hydrodynamics arises on the timescales when all these modes, even an odd, die out. And in 3D, that happens on the Landau timescale. In 2D, going to be different because the modes with even parity, they will die out as quickly as in 3D. The modes with odd parity will stay, and they will be long-lived. What we need to understand is how that behavior, how to understand that behavior when these modes are in the ergodic regime. They all, all the memory is lost, whereas those modes are barely begin to relax, right? So that's the unique aspect of the two-dimensional Fermi system. And so let me.
I had a quick question.
Of course.
So does this mean in a two-dimensional Fermi liquid, first sound is very robust, more robust than in a 3D Fermi liquid?
So first sound, you mean the density mode? Or
yeah.
I don't see why it would be more robust. I mean, the density mode is with us no matter what.
Okay.
But I mean, so I don't think it will be making the known hydrodynamics modes stronger, but we'll be introducing other modes, and they will have some interesting behavior.
Okay, I see. Thank you.
But maybe we can discuss it, again later. Maybe I don't understand the question. So yeah. Oh, that was Shankar. Hi. Hi. Didn't know it was you. Right. Okay. Good. All right. So let me just check how we're doing. Yeah. So maybe we spent quite a bit of time calculating the rates for these modes. It turns out that it's not just t square and t to the fourth for this modes and those modes. There's also some interesting dependence on the order of the angular harmonic, and quite a bit of analysis to do to calculate these rates. And so there is a long paper that we wrote on that topic, and I'm sure that it's just the beginning of a longer story, because it turns out that it's quite different than in 3D. In 3D, all excitations, deviations from equilibrium, relax at a t square rate. The only difference is the prefactor. And then in 2 dimensions, there is a wide variation of timescales, and so all of that comes out from the analysis. And maybe let me just review quickly what we know, and then proceed to discuss physics. So first of all, one can try to make that calculation with phase volume that we talked about more precise, and indeed you find that for the even periodic, for the head-on collisions that relax the even harmonics, you do find T square, and that just like in the Landau Fermi liquid, maybe there is some log prefactor here, but I don't think we care about prefactors. About log prefactors, we're after something bigger. But then for the odd parity modes, story is quite new and interesting. And if you, I mean, so let me first present a wrong, not completely wrong, but kind of wrong calculation. So if I do this analysis with small angle steps that happen in each collision, and say that it's the relaxation is kind of diffusion on the Fermi surface, and each step delta theta is what we estimated kBT over Fermi energy. Then based on that, I'll say that diffusivity is of order T square over Fermi energy that given by the rate by the Landau rate, and then in each collision I'm allowed to make a small angular step only, and then from that I can write down, I can find the relaxation rate as the time for Brownian walk on the Fermi surface, and that would give me plugging delta theta T of Fermi energy.
Leonid, sorry, quick question. Yeah. So I'm sorry, I think I'm just dimensions. I'm not sure I understand this. So these are rates, right? It should be T squared over T Fermi.
Yeah. So there is for.
Oh, I see. R is a like dimensional.
This is Ilya, right?
Right. Yes, me.
Yeah.
Hi.
Okay. I didn't see the picture, but I think I know how you sound. Yeah. So for people like you, there is a Rydberg, some kind of Rydberg constant here, which makes dimension right, and it's
all right. Yep.
It's an energy scale, but I mean one can. Yeah. So I think dimensions are not in doubt. What's in doubt are power laws, and
right.
so if you take that analysis, that predicts T to the fourth power law. Then if you start thinking more carefully, you see that potentially there are dangerous processes that may change the power law, and these dangerous processes occur when two particles collide nearly head-on. And the particles that collide nearly head-on, they are allowed to make bigger steps. If you think kinematically, then the angle for nearly head-on processes is not T over Fermi energy, it's square root of T over Fermi energy. So the angular steps here can be bigger, but the rate for these processes is still T square. And so you can ask whether that will be T cube or not. But then if you think of it more carefully and then do it properly, you find that I want to skip that because it will take too long. We wrote that humongously long paper where it's all explained, and it came out about a year ago. That the actual relaxation rates for the odd parity harmonics are still T to the fourth. The only thing that you gain out of these collisions which are neither head-on nor generic, the m square dependence of the order of the harmonic changes to m to the fourth. But that's I don't think that this will bother us today. It's interesting, but not for today's talk. But anyway, so one can my message is that one can analyze it pretty carefully and show that indeed for the even harmonics relaxation is like Landau predicted. For the odd harmonics, it's something quite different and much slower. But also there is some non-trivial dependence on the order of the harmonic, and there is a whole hierarchy. It's not just two different timescales. The whole hierarchy of timescales, different times for harmonics of different order, right? So that's okay. So then let me skip that and leave it for questions. One can discuss how it compares to microscopics. Then one can also, yeah, so then let me introduce two-dimensional systems. So the system, the two-dimensional system that has been studied most actively is graphene, which because it's atomically thin, electrons strongly interact. Electrons are in 2D, they interact with 3D, so they interact with Coulomb interaction, which is unscreened or is essentially unscreened, and so it is very strong. And in addition, so that's a good system to look for hydrodynamic behavior. And in addition to that, electron phonon scattering is weak, and also disorder is weak, and then symmetry, crystal symmetry is such that the Umklapp scattering is negligible. So all together, that makes it a very good system to look for effects of electron-electron collisions, in which in each collision, two particles conserve total momentum, but then they're allowed to exchange momentum, and that will generate shear viscosity. And so what people were interested in, people like myself and other people working on two-dimensional hydrodynamics were interested in, is what are the signatures of viscous effects and what are the new collective phenomena in this regime. And so there are quite a few papers that we published, and they're here. And I will, and then in graphene there are also several different regimes. There is a Dirac point where Fermi surface shrinks to 0, and then you have to you can think about hydrodynamics of gapless Dirac particles, or you can detune from Dirac point and go in the Fermi liquid regime that we talked about. One can detune in a different way and go to the whole Fermi liquid, and so all of that is under active consideration, both theoretical and experimental. And I will talk about one third of that problem. What happens if you have a Fermi liquid? Okay, and so let me skip this slide, which tells you on what length scales and at what temperatures we can look for hydrodynamics, and in order that's very important to try to plan experiments and understand experiments, because there are considerations for temperatures and for length scales, and all of that is important. But we can come back to it if there are questions. Right. So let me maybe one more slide, which is kind of part of the introduction. Let me just say briefly what we expect to see in a hydrodynamic fluid in 3 dimensions, and then compare it to our case. So in 3 dimensions, a picture is that on a microscale, the behavior is ballistic, and then after a few collisions, all the information about the microscopic state, except the quantities which are conserved in individual collisions, all of that memory about that is erased, and then on a length scale, few times the mean free path, the system transitions from that ballistic state, after the memory loss about all the non-conserved quantity, transitions to the orderly behavior that we describe by ordinary hydrodynamics, based on essentially conservation laws for these two conserved quantities, right? And then another system which is well known, where behavior is quite different, is one-dimensional fluids. And in one-dimensional fluids, collisions are such that even if they're happening very frequently, they don't produce any ergodic behavior, and we're very familiar with that. Staring at that toy and remembering how you play with it. The information is not erased at all, and that's a signature of an integrable system. So there is no hydrodynamic behavior in that system in the usual sense of word. There is no erased memory about microstate and behavior described by conservation laws. Now, what we have in 2D system is somewhere in between. So there will be quantities that will be erased, and then there will be quantities that will be conserved, and all together it will look a little strange. It will look like a mixture of this behavior and that behavior. Namely, there will be odd parity harmonics that will relax very slowly, and they will generate a quasi one-dimensional behavior that I will explain a couple of slides down, and that quasi one-dimensional behavior will generate angular memory, strong angular memory in the system, and as a result, there will be a hierarchy of timescales that I can describe by comparing it to the usual hierarchy. So the usual hierarchy, three-dimensional fluid, there is a ballistic regime at length scales and time scales before one collision, and then beyond that, all the memory except conserved constants is erased, and there are there is a hydrodynamic behavior based on conservation laws. In our case, two-dimensional Fermi liquids, there will be ballistic behavior at short distance, of course, and then on the length scale, time scale, when even parity harmonics relax and can be integrated out, it transitions to an effective to a new regime, which is described by an interesting combination of fully relaxed even parity sector and nearly unrelaxed odd parity sector. And in the odd parity sector, because of odd parity sector has an infinite number of harmonics, there will be strong angular memory in that sector, and more on that later. And because of strong angular memory, name tomographic is what we used for that, and that seems quite appropriate, because you have you can understand what's going on by considering slices in different angular directions, and then adding together the cumulative effect of all those slices to obtain response functions and so forth. And then at much longer time scales, greater than Landau time scale, essentially, system will transition to the normal hydrodynamic fluid described by Navier-Stokes. And so the interesting questions here are to understand these directional memory effects, and to understand the role of different scales, and what are the new equations of motion, and what are the manifestations, and so forth. So let me talk about some of that. First of all, if you want to really understand response functions, you want to do what we said: decompose distribution into even and odd parity components, integrate out the even parity ones, and then derive a response function based on the odd parity ones. And that can be done just starting from Boltzmann equation, linearizing it, and then doing a diabatic approximation in which you decompose timescales into long-lived and short-lived. The variables into long-lived and short-lived, and then integrate out the short-lived ones to obtain responses for the even ones. What you get after you do that, let me skip this analysis, describing this analysis, you will trust me, is that for the odd parity distribution, you get a one-dimensional, what looks like a one-dimensional diffusion equation, but the diffusion happens along the velocity direction. And velocity direction is not changing if you look at this part. It's changing very slowly due to relaxation of the odd parity harmonics. So there is some angular relaxation term here, but if you ignore that, then this will be really one-dimensional diffusion along the unchanging velocity direction, and the physical meaning of that will be clear clear in the next slide. But then if you put in electric field, you can calculate non-local conductivity, and non-local conductivity is also a way to calculate viscosity. And so what you find from this analysis that the conductivity and viscosity become non-local, meaning that they're scale dependent. And so it's not like an ordinary fluid where viscosity is a number. Depends on scale, like a non-Newtonian fluid. And a non-Newtonian fluid, viscosity is a function of thickness of the layer in which you probe viscosity. So from that point of view, it's an example, some strange example of a non-Newtonian fluid. And there are some power laws that you get for conductivity, current response to electric field, as a function of wave number, and that translates into some scale dependence. And there is a similar power law for viscosity, and P equal 4 describes the rate of angular relaxation of the for the odd harmonics, and so that gives some exponent, 3 2/3 or something like that, right? And so, and it leads directly to various interesting experimental predictions, and more on that later, but more on that in a moment. But before talking about that, I want to talk about the meaning of that one-dimensional diffusion that you discover after you do after you do separation of scales and in the Boltzmann equation integrate out fast relaxing modes. So let me consider following Gedanken experiment. Let me inject a particle in my Fermi C, and the particle would be a bump on the Fermi surface. That would be my test beam. Then convenient thing to do is to decompose this distribution into a statistical mixture of even and odd, like so, by adding a bump on this side and an anti-bump that with equal probability. Then after one collision that relaxes even parity harmonics, this will be gone, and we will obtain an interesting distribution in which there is a hole propagating opposite to the injected beam, and qualitatively, it looks like what we are used to in superconductors. It looks like back reflected hole produced by injecting a particle. So it's some kind of a stochastic Andreev scattering, and the physical meaning of that is pretty clear. If you inject a particle in the Fermi gas, it can collide. I'm not sure if I can show it with my finger. Maybe I should sit move away from the camera. If you inject particle, then this particle will collide with an ambient particle, which is in a head-on arrangement, and they will both scatter somewhere. But as a result, the beam, beam counter propagating to particle injected will become depleted of particles, so it will be populated with holes. And so that's the mechanism. You inject the particle, and then your particle and the ambient particle which collides head-on, they go somewhere, but as a result, you generate a beam of holes that propagate back to the source. And so that's the origin of that hole. And then notice that as a result of this collision, you do get some stochastization, but the angular memory of what you injected is not lost. You have a hole propagating back, and then what's going to happen next is that hole is going to collide with some ambient hole, and then by the same process, it will generate some holes that scatter sideways. But also there will be a particle will be propagating back to the hole. So there will be a particle that will be propagating in the original direction. So the sequence of collisions will produce like sequence of switchback processes in which particles transformed into a whole and the whole to a particle, and so forth. And that would happen indefinitely if there was no slow angular relaxation. Now, because of slow angular relaxation at the rate t to the fourth that we talked about, eventually it will die out. But there'll be a long-lived node which will look like electron-hole switchbacks, and that's the microscopic picture of of what these odd-parity modes do, right? So it's not, if someone thinks that Andreev scattering is a quantum mechanical thing, it's not true. It arises in many classical systems, and the famous red eye phenomenon in photography is of that kind, and then all the back reflection, retro reflection in various protective clothing that we're using, and etc. It's also that kind. So it is, if you like, it's what our Fermi system is doing. Our Fermi system is like an eyeball, that generates a red eye retro reflection, and that's that retro reflected hole. All right. So that's good. So let me. Okay. I mean, someone I'm sure will ask. I mean, are there any experimental signatures, and maybe we can talk about it later. It's also an interesting question how you use it to calculate response functions, and there is an interesting story about that. And the response functions, actually, the scale dependence that I advertised can actually be obtained from some continued traction formalism. But let me, so all non-local conductivity and non-local viscosity can be written as continued fractions, including those rates for relaxation rates for different harmonics. But again, let me skip derivations of all of that. One can analyze these expressions and derive those power laws that I advertised. Let's talk about manifestations. So if you have viscosity which is k dependent, and k dependence is as predicted by that approach, k to the power minus a third, then what do you expect to see, for example, if you do the standard Poiseuille flow experiment, when you take a pipe and push fluid through the pipe, and then, as we know from our school books, the velocity profile across the pipe will become parabolic. Now here, if you do it in a strip and calculate velocity profile, you get a fractional parabolic here. You get 2/3 power of Poiseuille flow, or something very close to that. And as a result, there'll be a deviation from Poiseuille scaling. There'll be a change in all other scaling relations that we're used to in the ordinary viscosity. So instead of 1 over k squared for conductivity, it will be 1 over k to the power of 5/3, and so forth. And similar for conductance, and all of that. So these exponents are new and interesting. They're not the same as in a conventional hydrodynamic behavior as you would expect. But also the velocity profile is different, because instead of the conventional parabola, we get velocity profile that looks like close to a semicircle. So blue line equals the parabola.
Sorry, Leonid, quick question. I mean, I missed what P was. I mean, you mentioned P equals 4 corresponds to something, but what are the different values of P? What is it?
P, okay, so 4, okay, maybe just, P equal 4 and not to keep it simple, let's focus on P equal 4. It's convenient, when you think about it, it's convenient to compare different models for angular relaxation. So what we believe is the correct model is what I described to you, P equal 4. that's when the gamma, the relaxation rate for harmonic of order m scales as m to the power 4, right? So that's non-trivial prediction of our.
So technically speaking, so p is the power of m in this formula. Is that?
Yeah, p is the power of m. So p
right,
p would be. Sure. No. Gamma m. Sorry, my pen is awful. But gamma m for the odd parity m would scale as t to the 4th, as we discussed, and there will be some dimensional prefactor, and then there will be m to the power p. And for us, because we originally thought that probably it will be just angular diffusion, and that would translate into p equal 2. It was interesting to compare the prediction for the normal angular diffusion and for what really comes out from the analysis. And what comes out from the analysis is p equal 4. And that's why so for historical or personal reasons, if you wish, we keep comparing all the time what happens in p equal 2 and p equal 4. But we believe that p equal 4, well, at least that's the outcome of that long paper that we wrote. P equal 4 is the correct answer. So blue curve is the Poiseuille parabola, and then the yellow curve is the p equal 2, and then the red curve is p equal 4. So it's somewhere in between, like semicircle and Poiseuille. Yeah. Okay. So we are. I think we're getting close to. Oh, someone wants to come in. Interesting. Maybe there's a next meeting here. Right. So good. So we are. Yeah. So from experimental point of view, let me just to make it more balanced, theory versus experiment. There are experiments going on trying to map out hydrodynamics on two-dimensional systems, and they are moving forward. And there are experiments in Weizmann Institute, for example, using capacitance probes, and they invented some ways, adapting some ideas from our paper how to map out velocity profiles in the systems, and they are seeing something, which looks promising. They take graphene ribbon, and at very low temperatures they see velocity profile, or they map out velocity profile. They don't see it directly. They map out velocity profile that looks uniform in the middle, and then some drops near the edges. But what that drop means, can be not sure how seriously we should take that into account. Could be a resolution problem. But then when they warm it up and go to what we would expect to find hydrodynamic regime, they see very clearly that there is a finite curvature region appearing in the middle. So it begins to look like a parabola of some kind. And I think at this point it's too early to say whether it's parabola or semicircle or something in between. But it's certainly something that will be clear soon. Likewise, there is a different technique using spin magnetometry that Amir Jacobi's group is using at Harvard, and they are also seeing something that looks like a parabola, but I mean they cannot. I don't think they have data of a wide range of temperatures. Also, their parabolas double hump often, and not clear what that means. But again, tools are there to test it, and I think that will be done. That will be done pretty soon. Okay, so I am at the end of that. I think. Let me just check yeah, so there are signatures of non-ohmic transport and non-local conductivity, so all of that is there. Yeah, so I think all of that can be safely, that's an old work that we did, not old, 5 years ago, work that can be safely skipped. So maybe let me just jump to conclusions if my slides allow me to do that. No. Yeah. Yeah. So anyway, so what we talked about is the new transport regime that you have because of the kinematic constraints in the two-dimensional Fermi gas that makes head-on collisions dominate, and they lead to many slower modes arising due to odd-parity harmonics of the distribution. And so the behavior is, you can say it's intermediate between hydrodynamic and ballistic, or if you translate it into response functions, you can understand it as a scale-dependent, as a system fluid with scale-dependent conductivity and scale-dependent viscosity, and you describe that by using, your phase space now is Fermi surface, which is distorted, but distortion is an odd-parity kind of distortion, like so. So these are loops in phase space with an odd-parity modulation, right. And then, so what's, why is it interesting? Well, of course, it's a new regime. It's a new regime, and a revision of a Fermi liquid, and as such, it is of course interesting for fundamental reasons. It is also interesting from the point of view of searching for electron turbulence, because if you do, I mean, people often ask, and I'm sure someone will ask when we start, taking questions, how big Reynolds number can be. And if you think about it from the conventional point of view, ignoring those slow modes, then the estimates give you Reynolds numbers which are not too impressive. I mean, you can get much bigger than 1, but not as high as you want to be in a really turbulent regime. On the other hand, because now we understand that in addition to the ordinary hydrodynamics density modes and momentum modes, there are also these multiple odd-parity modes which are very long-lived. That creates a new opportunity, because whenever you have a slowly relaxing mode, and even better, many of them, if you activate it, it will be long-lived, and during that long lifetime, any coupling, any nonlinear coupling, even if it's small, will have a long time to develop, and that will produce some nonlinear behavior, and basically that's how ordinary turbulence takes place. I mean, the two modes, density and momentum, don't relax, and as a result, even though the nonlinearity in the Navier-Stokes equation at higher order perturbation in velocity over a long time, it changes the behavior. And so all you need is to have the modes which are long-lived, and let them do what they want and interact with each other for a long time. So I think here we have a new opportunity for searching and finding new nonlinear phenomena. And again, that's interesting from fundamental point of view, but also one can discuss various applications. Maybe that is too far away at the moment. But people, if you're really serious about it, one can think about some kind of hydraulic logic that you realize by taking different jets that generate those slow modes, and then they interact or collide, and in this way you get switching behavior, like in logical gates. Yeah. So okay, I think the main. I think we're not trying to reinvent transistor. The main thing is that we have a new regime for two-dimensional Fermi liquids, and it's new and interesting, and many things are going to be discovered in that new regime. Good. So I think we're done, and thank you for and ready for questions. If there are any questions?
Okay, so if anyone has any questions, they can either unmute themselves or they can just raise my hand.
Joshua,
Hi. Good to see you.
Well, hi, how you doing? Yeah, well, once in a while, you encounter something that deserves to be called seriously cool. This is one of them. Great stuff. Extremely simple question. Like you were in school, why wasn't this figured out much earlier? This, sort of monumental addition to Fermi liquid theory.
Yeah, I don't know. I mean, if you think I didn't ask, if you think I didn't ask myself and I didn't search literature and so forth, no, I did search literature. I think somehow people missed it. I mean, why did people miss it? I don't know.
Just plainly overlooked.
People, but let me tell you. I mean, people. It's not that people didn't think this is. Didn't think about it. I mean, people did think about two-dimensional fermion systems, and many people noticed that there is something funny about two-dimensional systems. In particular, if you do a simple, this was somewhere very early. If you do a simple self-energy calculation to look at the quasi-particle lifetime, then normally you find t-square. In 3D you find t-square. In 2 dimensions you find that it's log enhanced.
Yep.
So all these all these people, they've been discovering that there is a log enhancement quasi-particle lifetime, quasi-particle decay rate, and then many people went further. Many people, like this paper, for example, tried to link that log enhancement with some kind of angular dynamics on the Fermi surface, and they tried, and then other people tried. So this is some people who worked on two-dimensional fermions. They realized that there was something interesting going on there, and they tried to look into it, and you can find quite a few papers that tried to understand it, but I don't think it got them a very clear picture. So the problem has been around. It's just
I know what you talk about.
Yeah.
It's just. I guess it's kind of an hairy analysis, right? To nail it down, that you have to have the kind of look to find how to figure it out. Or is it looking at even odd parity?
Yeah. Okay. I mean, it's combination. So the bits, and I should also say that there have been bits of what I was talking about that appeared in the literature so this understanding that head-on collisions play an important role. I mean, you can trace it back to quite far in the past. I mean, it's in some form it's Cooper pair scattering, right? But then connecting that to hydrodynamics, I think that maybe has not been done. But kinematically, head-on collision processes are favored. I think that has been, of course, very well known.
It could be just kind of historical development, right? That for a long time, these kind of people usually didn't very much about hydrodynamics, right? Because they were interested in electrons in solids, where Can't forget about momentum conservation.
Yeah.
I had to learn it rather late. That is all whole linear tradition of how you get from kinetic theory to hydro blah blah.
Yeah. Yeah. But okay, so maybe. Yeah, no, that's right. So let me maybe, because you asked this, let me just use it as an opportunity to advertise something. I mean, I talked about scale dependence, how conductivity and so forth depends on wave number. But one can also ask, what does it mean for temperature dependence? And so similarly to unusual powers for scale dependence, you also get predictions for unusual power laws for temperature dependence, which are different from what you expect from a conventional Fermi liquid, and that agrees with experiments. So there is this. The experiment is already there; it just hasn't been pointed out that the power law is unusual. So, for example, this experiment, which measured conductivity over constriction, a narrow constriction carved in graphene, and they see all the behavior that is expected based on hydrodynamics. In particular, they see that the conductance, when you go from ballistic regime to the hydrodynamic regime, conductance goes up, meaning the resistance drops, and so that's unusual, because usually when you introduce collisions, you expect that collisions will prevent you from conducting, and here they help you conducting. So that's a signature of hydrodynamics that we proposed and they found. But also, as part of that study that mapped it all out and showed that indeed resistance drops when you increase temperature, the temperature dependence of conductance of that constriction is not what you expect based on conventional Fermi liquid. It's what looks to me as pretty much like a linear temperature dependence up to a temperature where something else happens, phonons kick in. So here it's linear temperature dependence, and it's not a Fermi liquid. It's not a Fermi liquid T square that you would expect based on the conventional approach. It's a linear temperature dependence, and so that's indeed what comes out from that analysis. We believe that that's what comes out from this analysis with odd-parity modes which are long-lived. But of course, let me warn you, I'm sure you're going to ask right now, it's a linear temperature dependence for conductance, not for resistance.
Yeah. I started to get confused. I admit.
But it is a linear temperature dependence, very surprisingly.
Yeah.
And I think it's seen in experiment.
So I have a question.
It's not Fermi liquid-like. Yeah.
So I am Kevin Bedell. I have two points to make. One is back around 1999, I have a PRL that very few people have read about 2D scattering of spin waves. We were looking at spin diffusion, and we found the funny feature in it, which I was pushing, that it was something like a hidden conservation law, which was due to the funny scattering effects in 2D. And we also found longer lived modes, and there were a couple of additional modes. And so I had been working in that for 3 decades. And prior to that, just for Jan Zanen's education, I started looking into hydrodynamics in 1982. And I've had a paper that published back then, using it still now. We even did things we called quantum spin hydrodynamics, and because there was all quantum mechanical stuff in there. So some of us were doing these Fermi liquid things in 2D, and particular in the 90s. And it's when I'm interested in this, I forgot most of what I did in that paper. I just opened it up a few minutes ago. It's some of the things that you were talking about, scattering and all that. I've been looking at that in a number of cases. And this is kind of encouraging that I might go back again and look at this paper, because I think there is some connection to it. We're not doing, since we're doing spin diffusion, we don't have to worry about the Coulomb charge part of it that kind of makes things different.
Mm-hmm.
But it's more like for regular quantum fluid in 2D, and it's out there somewhere. I forgot the exact reference, but it's a PRL 1999.
Yeah. Please send me something to, or maybe put it on the chat if you, so that everyone can.
Just to say that this thing sounds to me, it's something similar, because there's the scattering processes, and I wish I had the kind of picture that you had in mind there in terms of what was going on, because it has a really neat kind of interpretation. What we did is we just kept doing the calculation and trying to figure out, what part of the integrals were doing what was causing some of the changes in the scattering rates.
Yeah.
So it's a pretty interesting problem, and it might even be good to look back in the past there. So.
Yeah, no, of course. Thank you for the comment. If you could please put it in the chat for everyone, or just send it to me by email.
Professor Levitov.
I'll send it to Joshua, and he can put it on.
Okay.
So can I ask some traditional questions about the talk? Hi, Leonid. So a couple of questions. One is sort of technical, the other is more conceptual. So when you have this M dependence of the rates for the odd modes, I guess when you increase M, I mean, you increase the rate. So is there in some sense, some cutoff related to the temperature beyond which those modes are not really long-lived anymore and you can forget about them? I mean, if you increase M, clearly, I mean, at some point, if you fix T over TF,
yeah, no, of course,
M overcomes it eventually, right? But maybe it's just unreasonably high values of M.
No, it's not unreasonable. It's where, where distinction. So if you go to M such that the rate for the odd parity mode becomes of the order of the rate for the even parity mode, that's where distinction between even and odd modes loses its meaning, and that's how sharp Fermi surface can be. I mean, Fermi surface is not infinitely sharp because of that M. The physically meaningful M values are limited, and they're limited exactly by what you said. You have to take M's which are somewhere where even and odd rates are comparable.
Right. Mm-hmm. Yeah. Okay, and hopefully it happens before you hit the K Fermi. I mean, I don't know. I mean, because that's the microscopic scale, the really granular nature of the Fermi surface, right? It's at the K Fermi level. I mean,
I don't understand that.
Well, sorry. I mean, yeah, no, forget it. Anyway, so another question was that, well, you mentioned that you can actually tune the Fermi surface by going to the Dirac point, right?
Yeah.
And I guess this whole story must develop in some non-trivial way, because there, of course, the Fermi surface is gone and something else should happen. So, I mean, is this something that you're working on, thinking about?
No, I'm not in a Dirac fluid business. I mean, people who are in the Dirac fluid business, they applied our technology, a diabaric separation of scales. They applied it to what's the Dirac point, and there were a couple of papers published, and you do see that the response functions become non-local, both in momenta and in there is a strong K dependence. I mean, not as strong as in our case, but there is some anomalous K dependence, but also there's some non-locality in angles. So all of that happens at the Dirac point, but I think I'm happy to let other people
No,
do it.
but there must be some crossover, right? I mean, if you just gradually change things, then you should.
No, I'm
see
sure there'll be some crossover. I mean, I mean, the reason I'm not well, I think there is a big community working on what happens with the Dirac point, and I think they should,
right.
they'll be able to figure it all out, and I think much better than I will do it. Also, because my interest is in long-lived modes, because I think long-lived modes are good for something, for turbulence, nonlinearity, whatever. You get longer-lived modes. So you see, the unusual thing here for me is that you can get modes which are longer-lived than what Landau ordered, right? So you can get modes which live beyond Landau dissipation timescale, and so that's interesting, because that is, I mean, for a number of reasons, but also as a potentially as a way to get some non-trivial nonlinear behavior and so on and so forth, and so that I think for that, I think going too close to the Dirac point is not so useful. And you need to, I mean, you need strong interaction, so you need to be somewhere near the Dirac point. But going exactly at the Dirac point will make all the modes, decay at identical rates, and then we'll lose the structure. But I agree that from a fundamental point of view, it's interesting to see how the multi-scale structure that you get away from Dirac point turns into a single scale structure on a Dirac point, and so that's something that we'll probably figure out in the future. I mean, at this point, people just looked at what happens at the Dirac point and sufficiently far away from the Dirac point, in the sense that KBT is much smaller than Fermi energy, and there's no picture in between. But I'm sure it will. It will be found. Yeah.
All right. Thank you.
May I ask one more?
Absolutely. Yeah.
Thank you. I've been trying to think about whether there'd be any interesting interplay between this directional memory and a magnetic field applied perpendicular to the plane. Have you thought about that? And one might say that perhaps it just washes everything out by running the modes around the circle into each other. But I was wondering if one spatially modulated the field or something. Is there some interesting crosstalk?
Well, okay, so that's something on the back of the mind, and we are looking into that. But as of now, I don't think I have anything striking to report. Well, the only thing maybe that is related, let me show you. There is a preprint that we wrote on the following subject. So if you, I'm not even sure. Sorry, this slide is not here. But let me just wave my hands. So you can ask how do you see this backscattered retroreflected Hall? And as we know from Andreev reflection on superconductors, magnetic field helps a lot, because when you apply magnetic field, Lorentz force deflects holes in the opposite direction from the particle, and then the retroreflected Hall will not be retracing particle trajectory. It will be deviating from particle trajectory, and that breakdown of retroreflection introduced by magnetic field is a very clear signature of Andreev transport in superconducting systems, and so one can try a similar idea here and consider signatures in magnetotransport due to a magnetic field separating retroreflected Hall from the particle, and indeed it works. There is some regime where there is some unique magnetotransport effect, some change of something of non-local potential, which is induced by very, very small magnetic field. And so that's something that we predicted, and maybe people will look into it experimentally and hopefully tell us whether it's there or not. But yeah, magnetic field can be useful in a number of ways. Yeah, that preprint is on the archive.
Thank you.
Yeah.
Okay, so if not any more questions, maybe let's thank Professor Levitov one more time.
Yeah, well, thank you. Thanks a lot for arranging it.
You're welcome.